And this brings us to part 6. Problem 6 says a function f has derivatives of all orders for -1 less than x less than 1. The derivatives of f satisfy the conditions above. The Maclaurin series for f converges to f of x for absolute value of x less than 1. Show that the first non-zero terms of the Maclaurin series are given by this. So let's see. I know that f of 0 is 0, f prime of 0 is 1. If I want f double prime, that means n is 2. So this is -2 times 1, which is -2. If I want to find the third derivative, that means that n is 3, so this is -3 times my previous derivative, which is 6. And I can continue in this idea. The fourth derivative, n is 4, so this is -4 times 6, which is -24. I can keep going with this pattern. But remember that a Maclaurin series is going to be the sum of the nth derivative at 0 times x to the n over n factorial. So for us, the first 4 non-zero terms are going to be, well, there's my first non-zero term. That's going to be 1x to the first over 1 factorial. Here is my second term. That's going to be -2x to the second power over 2 factorial. Here's my next term. It's going to be, did I do that right? I didn't do it right. And this brings us to problem 6. Problem 6 says a function f has derivatives of all orders of magnitude for -1 less than x less than 1. The derivatives of f satisfy the conditions above. The Maclaurin series for f converges to f of x for all absolute value of x less than 1. It says show that the first 4 non-zero terms of the Maclaurin series are given by this, and write the general term. So remember, the Maclaurin series is the sum of the nth derivatives at 0 times x to the n over n factorial. So I need to find these derivatives, and luckily they've given us a start. They told us that f of 0 is 0, f prime of 0 is 1. So if I want to find f double prime, that means that n is 1 for my purposes. And so it's going to be -1 times my previous number, which is -1. If I want to find the third derivative, here n is 2. So it's going to be -2 times my previous answer, -1, which is a +2. And if I want to find the fourth derivative, n is 3. So this is going to be -3 times my previous answer, which is -6. And so now I'm ready to add the terms. So keep in mind that my function, f of x, is going to be equal to, well, my first 4 non-zero terms, which means I really don't care about that term. So the first term I come up with is going to be this 1, x to the first over 1 factorial, plus I'm going to have -1, x squared over 2 factorial. My next term is 2, x cubed over 3 factorial. My next term is -6, x to the fourth over 4 factorial. And this is going to continue on. So I really have x to the first minus x squared over 2 plus x cubed over 6 minus x, excuse me, not 6, that's just a 3, because that's 3 factorial, which is 6, divided by 2 is 3. This is minus x to the fourth over 4 plus, and this is going to continue to x to the n over n times -1 to the n plus 1. Notice that my even terms are the ones that get the negative signs, and my odd terms are positive, plus ... So I need to make sure that I show that I get the first 4 non-zero terms, my work here, and then I need to also show my general term. On B, it says determine whether the Maclaurin series described converges absolutely, conditionally, or diverges at x equals 1. Keep in mind that my series evaluated at 1 is going to be 1 minus a half plus a third minus a fourth plus a fifth minus ... And this is an alternating series test, so this converges. But if I want to look to see if I'm converging absolutely, we converge absolutely if the sum of the absolute value of the terms converges, which doesn't happen because this ends up being the sum of my terms, which is 1 plus a half plus a third plus a fourth. And this is a harmonic series. So this diverges. So the Maclaurin series converges conditionally at x equals 1. So again, I have to do that conditional convergence test. Test the absolute value of the terms to make sure they converge. If they do, great, I converge absolutely. But they don't in this case. So, moving on to part 3. Part 3, they want the first 4 non-zero terms and the general terms of the integration of this. So keep in mind that f of x, as we wrote it, was x minus x squared over 2 factorial plus x cubed over 3 factorial minus x to the 4th over 4 factorial plus stuff. And remember, I had negative 1 to the n plus 1 x to the n over n. So if I want to find g of x, I'm going to have to integrate each of these terms piecewise. So integrating this term gives me x squared over 2. This is going to give us x cubed over 3 times 2. Ooh, horrible, horrible, horrible. It was just 2. It was just 3. It was just 4. Plus x to the 4th over 4 times 3 minus x to the 5th over 5 times 4. And I'm noticing a pattern here. I notice that I still have an alternating series, but my odd terms now carry the negative sign with them. And my denominator is always going to be the product of whatever my exponent is times the number that's 1 less than it. So there's my general term of my Maclaurin series. And now moving on to the last problem. So the last problem says let p of n of 1/2 represent the nth degree Taylor polynomial at x equals 1/2, where g is the function defined in part C. Use the alternating series error bound to show this is true. Remember that from the alternating series bound, I know that my error is going to be less than the absolute value of what we call the next term. Now for us, because we're talking about a 4th degree polynomial, n is 5. So I want to know what's happening with that 5th term. Now my 5th term, my 5th degree term, keep in mind, is this x to the 5th over 5 times 4. So for us, it's going to be 1/2 to the 5th over 5 times 4. So that's going to be 1 over 2 to the 5th times 1 over 20, essentially. So I have 1 over 32 times 1 over 20, which is 1 over 640, which is definitely less than 1/500th. So I'm using this alternating series test because my series alternates. We saw that from the previous problem. We've seen it twice because of this alternating sign part. And the terms do get smaller and smaller progressively. So we satisfy all the conditions of the alternating series test. We know that g is alternating, and g sub n plus 1 is less than, or I should say a sub n plus 1 is less than a sub n for g equals the sum of a sub n x to the n. So because it satisfies the things we need for the alternating series error bound, we can show this inequality.